me from Guangzhou, China. I'm working at the Center for Stem Cell Biology and Tissue Engineering. Key laboratory for stem cells and tissue engineering. Ministry of Education, Sun Yat-sen University. Today, I will be talking about using stem cells and lineage reprogramming technology to treat cortical fibrosis. Heart failure usually happens after cortical fibrosis sets in. It is a big problem with high incidence and mortality, right that keep increasing every year. The main issues are the co-pathologic features and the factors driving heart disease, like myocardial infarction and heart failure. Unfortunately, there aren't any definitive cure available yet because virus cells get involved leading to excessive activation of fibrosis and score collagen deposition. This full process starts with different stimuli like myocardial injury, inflammation process, or mechanical strain triggers it. The cascade of fibrogenesis is thought regulated by different signal pathways involving various cell types. However, we are facing challenges due to the lack of suitable models for disease modeling and high throughput drug discovery, which makes it difficult to establish effective treatments for cortical fibrosis. Obtaining human autologous heart cells is taught, while two-dimensional heart cells lack a proper structural organization too. We are still waiting for a breakthrough in anti-fibrosis drugs. Researchers have utilized different types of cells, like HMSCs, HESCs, and HIPSCs, to target damaged heart tissues and promote its repair and regeneration. Extensive preclinical and clinical studies have shown the potential of MSCs transplantation in protecting against various cardiovascular disease, such as acute myocardial infarction, both ischemic and non-ischemic heart failure, hemic therapy-induced cardiomyopathies, and myocarditis. They also offer benefits in terms of anti-fibrosis, anti-inflammation effects, preventing cell death, immunodonation, and promoting blood vessel formation. Stem cell technology combined with reprogramming techniques can help alleviate cardiac fibrosis, as discussed in this review. Developing models for cardiac fibrosis using stem cells is a crucial aspect. The progress made in stem cell technology has facilitated this creation of models for study cortical fibrosis over the two past decades. Within reduced pluripotentia, stem cells have been due to self-renew and differentiated into various cell types. It has become possible to produce large quantities of targeted cortical cells in vitro. Building upon this advancement allows us to think a three-dimensional structure that closely resembles an authentic heart. Our laboratory specializes in constructing engineered human myocardial tissues where assessing is contrasted. We used chemical programming techniques to prepare cortex tissues from human adult cells. We have developed a new method for making corticosteroids that are highly pure, over 90%, without any animal sources or unclear chemical composition, and without adding foreign protein growth factors. It is also cost effective, with less 500 yuan for 100 million cells. Additionally, we collaborated with Professor Zhang Donghui from Hubei University to create human heart organoids for repairing infected hearts. We constructed and evaluated functional human stem cell derived cortical glide that showed good contractility, their microstructure, and electronic conduction characteristic. By using human stem cell derived cortical glide, we stimulated the process of myocardial damage repair fibrosis seen in real hearts. In this movie, you can see the scarring after heart glide damage, where the damaged tissue clearly show fibrosis as indicated by Mason Stanley and Abbas May Stanley. Building our previous work, we conducted heart support screening of anti-fibrosis drugs using a fibrosis model based on human cortical glide. We established a high throughput drug screening platform and developed an instrument to evaluate electronic conduction and cytotic function of human cortical glide efficiently. Based on this result, we screened a small molecular inhibitor called PI543, which demonstrated significant antifibrotic effects in various models. For example, treatment with PI543 effectively stops fibrosis after injury to cortical glide. PI543 significantly reduces the damage to cortical glide by inhibiting fibroblastic activation and reducing levels of fibrosis. Additionally, PF143 enhances the contractility of damaged heart organoid. Another aspect for treating cardiomyopathy is through their reprogramming techniques. Cardiac fibrosis can be directly transformed into cardiac-like cells in vivo using microRNA, transcription factor, and small molecules to achieve in-situ repair of cardiac tissues. Furthermore, cardiac fibrosis can also be indirectly reprogrammed into cardiac progenitor cells using small molecules in vitro, which can be then be used for transplantation or differentiated into various types of cells. A large scale for cell transplantation, disease modeling, and patient-specific sample biobanking. For instance, our research group has successfully transformed human fibrous into functional cardiomyocytes, known as chemically induced cardiomyocytes or CICMS, using a combination of line small molecules along with two inhibitors targeting platinum drive the growth factor receptors. These CICMIs closely resemble human cardiomyocytes in terms of transcriptal analysis, epigenetic features, and innate physiologic properties. This discovery nicely groundwork for potential in-suit repair of the heart through targeted modulation of endogenous cardiac fibrosis using small molecules. Using a similar strategy, we recently reported the generation of CICAPs from mouse and human fibrosis. The CICAPs poses multi-potential to differentiate into various types of cardiovascular cells using transgene-free reprogramming approach involving 6 small molecules. Subsequent transplantation of the CICPs into infected mouse heart result in improved animal survival and cardiac function for up to 30 weeks post-infection. Despite the considerable potential of stem cell therapy in addressing cardiac fibrosis, there are still several obstacles that need to be overcome. The major bottleneck is targeted delivery of anti-cortical fibrosis drugs. Limited effective drug concentration and duration within the heart result in suboptimal therapy effects. Most clinic trials have failed due to systemic hepatic and renal toxicity, leading to significant toxic side effects on their organs. We have designed a targeted drug delivery system based on nanomaterials. I designed targeted nanomaterials for drug encapsulation is among the most promising drug delivery systems that are available today. After a heart attack, increased reactive oxygen species out of the cortical redox environment. Well, though they never observed such changes in the heart after myocardial infection, we found that after heart attack, the levels of GSH increases in cardiac fibrosis. So we designed and synthesized CYS8E nanoparticles for targeted drug delivery that respond to GSH. Efficient and targeted drugs released for post-heart attack using CYS8E nanoparticles was achieved. The invasively infected fluorescence imaging show that mice treated with 3DIR had hardly detectable fluorescence signals, whereas those treated with DIR-MPS had strong and stable signal 12 hours after injection. This suggests that CYS and the MPS enable robust and sustained release of drugs in vivo. CYS8E nanoparticles were used to deliver drugs specifically to cortical fibrosis after a heart attack, since these cells have had levels of cysteine transporters. They efficiently load antifibrotic drugs into civilized nanoparticles and demonstrated that their GSH-dependent release by preparing PF 543 loaded nanoparticles. Those PF 543 nanoparticles is haploid good stability, responsiveness to GSH, and compatibility with the blood. In summary, since therapy for cardiovascular is an advancing field with a promising prospect for the future. Ongoing research and technology advancement are driving the development of novel anti-cortical fibrosis drugs. Finally, I would like to express my gratitude to Professor Zalan for his guidance, our collaborators, as well as the National Foundation Commission, the Ministry of Science and Technology, and the first affiliated hospital of Sun Yat-sen University for their foundation support. Thank you all for your listening. We look forward to potential collaborations.